Yes.
Okay,
Yes.
so for those who don't know me, my name is Aryan and I'm a student. And for today, our discussion would be about entropy. So, entropy is a measure of disorder or randomness in the system. It plays a fundamental role in the second law of thermodynamics. Understanding entropy helps explain the evolution of physical systems from gases to cosmic objects. So, entropy uh, it was invented to solve a problem for getting more efficient uh, steam engines. So people observed that the steam engines only convert 1% of the energy that they burn by coal into actual work. So to overcome that, they invented entropy to understand the heat flow and where is that excess heat going. So, some historical background of entropy. So, this concept was introduced by Rudolf Clausius in the 19th century. It was initially developed to describe heat transfer and irreversibility. The term entropy derives from the Greek word entrop, meaning transformation or the point of no return, and it was deliberately made to sound like energy. So thermodynamics foundation, entropy quantifies the numbers of microscopic configurations consistent with a system's macroscopic state. It increases in spontaneous processes, indicating the direction of natural evolution. The second law states that the total entropy of an isolated system never decreases. The picture that we see is it's an T page curvature. So we'll talk about this in our later in the presentation. So this picture is about the entropy of a black hole. Uh, there are two main people here, Hawking and Don T page. So we'll talk about this picture later in the presentation. So let's get to the thermodynamical laws. So uh, we will be talking about the thermodynamical laws, and then what effects does it have on black holes and their entropy. So the zeroth law of thermodynamics states that if two thermodynamic systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. The zeroth law of black hole mechanics states that a stationary black hole has a constant surface gravity across its entire horizon. So this directly mirrors the classical zeroth law of thermodynamics, where an object is in thermal equilibrium, has a uniform temperature, establishing a surface gravity has the geometric analog of physical temperature. So the effects that it has on the black hole is that it says that the black hole must have uniform temperature and surface gravity. So the first law of thermodynamics. So it's a fundamental principle stating that energy cannot be destroyed or created, only transformed from one form to another. It establishes that the total energy of an isolated system remains and constant. The first law of black hole mechanics is a statement of energy conservation. It dictates that any change in black hole's mass directly balances in its horizon area, spin, and electric charge. So this perfectly mirrors classical thermodynamics, mapping mass to energy and surface area to physical entropy. Okay, so the first law states that energy cannot be destroyed or created. It goes into one form or another. So in uh, what what effects does it have on the black hole is that if it gains something, its consequences are seen. Otherwise, when a black hole gets some mass, what happens that its event horizon increases a little bit, and with that, if the if I drop something into the black hole, it also has entropy, and that entropy the black holes gains that entropy, and that is seen in the event horizon area expansion. So if I drop something in it, what happens, the black hole, the event horizon expands, and the event horizon contains all the entropy of that black hole, which is also known as the holographic principle. I think so. Someone wants to say something. Your voice is not clear. I think so. We should move on to the second law. Okay. The, the second law of thermodynamics states that the total entropy, a measure of disorder or randomness of an isolated system, will always increase over time. The generalized second law, GSL, states that the universe total entropy cannot decrease, formulated by Jacob Bekenstein. It combines black hole geometric area with surrounding matter and radiation. And while Hawking radiation causes a black hole to shrink, the escaping particle creates greater external entropy, ensuring the total net balances always increases. So, Hawking radiation. So, we had to change the second law of thermodynamics, and now we have the generalized second law, GSL, which states that the universe total entropy cannot decrease. It means that what was the flaw with the second law is that uh, what happens right now is that uh, if I have a place, its local entropy will decrease, but the universe's entropy would never decrease. So if it's locally decreasing, something is happening that increases the entropy of the whole universe. So uh, yeah, this is why we needed the generalized second law, which states that universe's total entropy cannot decrease. So, if a black hole had zero entropy, and uh, if we dropped something into it, what does that mean? Is that the whole universe's entropy decreased, and that's not the case. And so then, so now Jacob comes in and says that the entropy, a black hole has entropy, and it's encoded on its event horizon, and and it's all. And now comes the GSL, which states that the universe's total entropy cannot decrease. So uh, let's take a real life example. If I put some ice into the refrigerator, what happens is it's that it becomes ice. It becomes more ordered, but uh, what happens is that the refrigerator has to do work to make that ordered state, which means more entropy increase. So this is the second law. So, ladies and gentlemen, do you have any questions? Okay, there was a question. Can you please explain the zeroth law, like in the case of a black hole? So, okay, so go ahead. Okay, I think so. We should go ahead. Okay, we'll take that question at last. So, the third law. Okay, there's another question. How comes universe's entropy decrease if I drop a pen in black hole? The major thing is that it does not decrease, but with our previous laws and previous understandings, that was the case. So that is why we have generalized second law, which states that the universe's total entropy always increases, so it never decreases, and that dropping the pen into the black hole, what happens is that now with our current understanding, we know that a black hole also has entropy. So it's not like it does not have any entropy or stuff. It does have, and it's the most efficient entropy generator because it has the maximum number of hidden configurations. So that leads to higher and higher entropy. So I think so. We should head to the topic. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, the entropy of a perfect crystal approaches a constant minimum. The, the third law of black hole mechanics states that it is impossible to reduce a black hole's surface gravity to zero through any finite sequence of steps. This directly mirrors the classical third law of thermodynamics, providing that an external black hole, the geometric equivalent of absolute temperature, can never be reached. So, what it says that the third law says that we can never achieve an absolute zero. There is an minimum cutoff that it will reach and not continue further. And there's the case for thermal black holes. So, what happens is that uh, there are two things, microstates and macrostates. And we do not have any generalized form of the equation for macrostate. It is just we have three variables: the total number of particles, and in the black hole's case, the mass, charge, and spin. And when we have that, and if the charge and the spin more, what happens? More uh, are more. What happens is that the entropy of that specific black hole decreases. What I'm saying is that in the core, if there are a lot of like charges, they would repel each other, meaning they would get to a more disorganized state, which means lesser entropy. And the spin, also the spin part, what happens is that because a black hole spins so rapidly, what happens is that it gets bloated into the center, and which reduces its total entropy. And this these are dictated in general relativity. So there are few equations in general relativity that describe it, and an external black hole is what it's the equivalent of reaching absolute zero temperature. So we do not have external black holes, but we have very close to them, which have a very high amount of charge and high amount of spin. An external black hole has an entropy of 2 pi times mass squared, but for a normal black hole, what's the case is that 4 pi mass squared. And we'll just talk about these equations later on. But what happens is that it gets halved. The entropy gets halved when at the case for an external black hole. Okay, could studying a black hole thermodynamics help us develop a theory of quantum gravity? So, yep, there's a paradox. There's a very famous paradox in black hole about black holes is the information loss paradox. So, what's the case? We need an unified theory. So, studying these can help us have some more insights about how would that theory look like. So, and mathematical Definition of entropy. Entropy is given by the Boltzmann equation. S is equals to KB times logarithm times W, where KB is Boltzmann constant and W is the number of microstates. This formula links microscopic states to macroscopic thermodynamic properties. So I'll just talk about these microscopic and macroscopic things right now. And macrostate is like if I have a square which has 100 compartments and 10 and there are 10 particles in total, the macro state is what it is 100, it's 100 squares, the compartments that they can take, and there are 10 particles and the energy. So that is the macroscopic macro state. And the W is the number of microstates. And if we want to calculate that, we have an equation for that. We need the number of compartments that each particle can have, which is 100 factorial. So and factorial is just like if I have a 10 factorial, it would be 10 times 9 times 8 times 10 till 1. So 100 factorial divided by 10 factorial times 100 minus 9 10 factorial, and we'll take that. So the W is the number of microstates, and uh, after that what would after that we'll get it, and after doing the logarithm and stuff, we'll get the total entropy, which would be I think so about 38 Boltzmann constant. So it's a very huge number. The calculation is very vast. So and as we said that the the isolated and in an isolated system the entropy always increases. So it means that we are starting from a very close space, like in a very packed state, and then what happens is that the particles start to move and stuff. So that results to entropy increase. Measuring entropy in classical systems. So entropy can be measured experimentally through heat transfers and temperature change. In ideal gases, entropy change is calculated from initial and final stages using thermodynamic equations. Uh, calu- Calorimetry is a common method used to determine entropy change in laboratory settings. Calorimetry, so uh, uh, what it's a study of temperature changes in chemical reactions and stuff. So it's a study of that, and it's pretty used in determining these entropy changes in. So okay, entropy in statistical mechanics. So it connects microscopic particles behavior with macroscopic entropy. It interprets entropy as the logarithm of the number of accessible microstates. This approach provides a deeper understanding of the nature of disorder. So we just to get that entropy, we took the logarithm of the number of accessible microstates. So uh, the amount of microstates is also is the entropy divided by the Boltzmann constant, and the entropy would be if I have 400 entropy, and what we'll do is that we'll divide it by the Boltzmann constant, and after doing that we'll get 100, and if we just plug in that, what we'll get is that e raised to the power of 100. So that is still a very uh, huge amount of entropy, and we'll plug it into the equation and get that. Entropy in stars, basic concepts. Stars evolve through processes that involve changes in entropy. During nuclear fusion, entropy increases as energy disperses. the balance of entropy influences stellar stability and life cycles. So it can be the picture that we see. We see the change in entropy is equals to Boltzmann constant times the natural logarithm of the number of microstates. So, but in stars, it is a little complicated because the density of gas and the other things, there are many particles, and the particle density in gases is it's like if we have a cake and there are many layers in that cake, and each layer's density, the amount of particles in it is different. So we have to get the entropy of each system and add that. So it's a little complicated. So stellar entropy calculations. So entropy in stars can be estimated using thermodynamic models for stellar interiors. It involves temperature, pressure, and composition profiles. Numerical simulations help quantify the entropy changes during stellar evolution. So, so in the picture, we see a lot of equations. They are about mass conservation, energy equations, and their radiative transport. So when a star like a massive when massive stars die, they can become a neutron star or a white dwarf. But what's the case with white dwarfs and neutron stars? It is that they are highly ordered. It means that the entropy just decreased, but that's an local decrease. But and in that transaction, the star becoming a neutron star, what's happening is that it's also radiating gas and other things into space, which are indirectly increasing the universe's entropy. Entropy and stellar evolution. So as stars age, their entropy generally increases due to energy dispersal. When stars exhaust their nuclear fuel, entropy production accelerates. The entropy budget influences phases such as red giants, white dwarfs, and supernovae. So, in the picture given, we see the difference between black holes and normal systems. Uh, what happens is that uh, the x and y axis, it's the entropy and the radius of that particular system. And in the black hole case, the entropy increases with our area, and the normal systems it increases with volume. So there's a huge difference. The entropy of a black hole increases exponentially with its mass. So, entropy in stars microstate perspective. In principle, the entropy reflects the number of microscopic configurations of particles in star plasma. Due to complexity, direct microstate counting is challenging. So, thermodynamic models are typically used. Entropy increases as stars fuse lighter and lighter elements into heavier ones, which increases disorder. So, as we know that we cannot take in account for trillions and trillions of atoms, and with this equation, what's the case is that if I have to measure the entropy for a glass of water, I have to look into the every atom and every molecule of that specific water. But there's another equation which is about black holes, which is like looking far away from a chimney and determining its temperature. It's just like that. So we are doing it from far away, and this uh, like we do not know the microstates in the black hole. How would know? We don't know about the microstates in the black holes. So there's another equation that we use to get that, and it uses string theory and quantum mechanics to count the numbers of microstates in the black hole. So, uh, okay, there's the Bekenstein Hawking. It's about black holes entropy. So a black hole's entropy is equals to area times c cube divided by 4 times h bar times g. The difference between h bar and the normal h that we see, the Planck's constant, is that h bar is equals to h divided by 2 pi. So if we just as we know that area is 4 times pi times r squared, and the Schwarzschild radius, we are just taking the Schwarzschild radius, which is right now 2 times gravitational constant times mass divided by c squared, and we have 2 squared that, which then we'll receive 16 times pi times uh, gravitational constant times mass squared divided by c, c raised to the power of 4. So there are many equations describing the entropy of an black hole, but they all are the same. It's just the measurements and the variables that we use. So a black hole's introduction. So black holes are regions of space-time with extremely high density and gravity. So they challenged traditional notions of entropy and thermodynamics. The study of black hole entropy links gravity, quantum mechanics, and thermodynamics. So now we are going to the black hole part. So the study of black holes entropy, it links to gravity, quantum mechanics, and thermodynamics. And to get the entropy of a black hole, we measure the number of microstates uh, using quantum mechanics and string theory. So and one more thing is that the entropy of a black hole is not stored within its center or anything else, but it is stored in its event horizon. So it depends on the surface area of the event horizon. So if I drop something of high density, what happens is that uh, the event horizon gains some more area. And but the thing with black holes is that they are they completely destroy that thing and store it as whole entropy. So like the thing got crashed and its entropy is now stored inside the event horizon. So so there comes the information paradox, like about the Hawking radiation. It radiates, and that radiation is seemingly random. It does not have to do anything with with anything that is inside that with the entropy. So if I drop an apple, what happens is that the entropy of the apple gets stored into the event horizon, but the Hawking radiation is seemingly random. It's just thermal radiation. It's not the specific uh, atoms or the configuration of the particles inside that apple. So it seems like the information has been lost. So it's like crushing up paper, like a shredder. A black hole is like a shredder, and if I put something like an apple into it, completely shreds it, and it which seems like the unique information has been lost. So which is against quantum mechanics laws. So Stephen Hawking also said that quantum mechanics seems to be fundamentally broken. So we'll talk about the information paradox at the end of the presentation. So the key is determining the event horizon area. So uh, A, which is A, and which depends on the black hole's mass, charge, and angular momentum. For a non-rotating uncharged black hole, its area is equals to 16 pi g squared m squared time divided by c raised to the power of 4. And if we just plug it that into the equations shown in the picture given, what will get is that kb times cq divided by 4gh times 16 pi g squared h squared divided by c raised to the power of 4. And if we just cancel those equations, we'll get uh, 8 pi squared uh, times the gravitational constant times times kb, the Boltzmann constant, and divided by 2g h bar. So if we want to get rid of the h bar, what we'll do is that we'll multiply the numerator by 2 pi. So that is how we calculate black holes entropy, measuring black holes entropy. So direct measurement of black hole entropy is not possible. It is inferred from horizon properties. Astrophysical observations from black holes support uh, theoretical entropy estimates. The entropy concepts helps explain black hole thermodynamics and Hawking radiation. So there's one thing called a Bekenstein's bound. So it says it is the limit of storing information. It's the limit, and that limit, when something reaches that limit, it is known as a black hole. And to get the maximum entropy of any object or any system, we'll just use the Bekenstein's formula. And for our universe, it's about 10 raised to the power of 123 Boltzmann constant. So it's still it's a lot, and I think so. We are standing about 10 raised to the power of 105 or 106 something. So we still have lot entropy to go before we die of heat death of the universe. And black holes store the most amount of entropy because it has the maximum hidden microscopic states. So an object, like if we assume a star and a black hole with the same properties like mass and other stuff, what happens is that the black hole has about 10 raised to the power 40 something factors more than the star. It's exponentially more. And that's the special case for black holes. And most of the entropy in a universe is are of black holes. So they contribute to about 99% of the entropy of the whole universe. Bekenstein Hawking entropy. So the entropy of a black hole is proportional to the area of its event horizon. The Bekenstein's Hawking formula is SBH is equals to KB times C cube times area of the event horizon divided by 4G H bar. And H bar is just the Planck's constant divided by 2 pi. This indicates that black hole entropy scales with surface area and not volume. Okay, so uh, this so and there are few more interesting properties of black holes. With I think so. We are going to talk about the black hole mergers and their entropy. So uh, as we know that if we combine two systems, what happens is that the the third the product of those systems would have more entropy uh, than both of the systems combined. So we'll just talk about that further. So significance of black hole entropy. Black hole entropy suggests a deep connection between gravity and quantum theories. It implies that information about matter falling into a black hole is encoded on its horizon. This concept is crucial to understanding the black hole information paradox. And yep, one more thing uh, about the Hawking radiation. So, what happens is that with time, Hawking radiations get more and more, and the reason for that is this Hawking radiation is inversely proportional to mass squared. So it means the more the mass, the lesser it radiates, and the lesser the mass, the more it radiates. So it sets off a chain reaction, and if you're just wondering why it's the case, it's because smaller black holes, there's the tidal forces at the event horizon gets larger and larger. So if I would just want to give you an example, if I go near a black hole, smaller black hole, what would happen? The death zone, the place where I would just get crushed in some, would be more, would be uh, like earlier than a bigger black hole. So a bigger black hole is like a gentle beast; it would kill you, but not very fast. So that is why smaller black holes radiate more and more Hawking radiation. Black hole thermodynamics. So black hole obeys laws analogous to the thermodynamic laws. The second law states that the total entropy, including black hole entropy, never decreases. Hawking radiation leads to black hole evaporation, decreasing entropy over time. So the second law states that the entropy of the black hole must never decrease, but due to Hawking radiation, it decreases. So that is why we have the generalized second law, which states that the universe's entropy should never decrease. So that's the case with Hawking radiation. Entropy and information paradox. So the black hole information paradox questions whether information is lost when matter falls in, and resolving this paradox involves understanding how entropy and information are related. Modern theory suggests that information might be preserved in a quantum form. So, one more thing I wanted to say is that one quantum bit of information is stored on 4 pages of blank area. So, and this about this entropy and information paradox, it's like if I drop a diamond into a black hole, it's specific, like the specific arrangements in the diamond are lost to us. It just gets destroyed and stuff, and it gets stored on the event horizon. But the Hawking radiation, uh, like around the Stephen Hawking says that the radiation is completely random, and it's just like thermal heat from coal and stuff. So it's not related to the uh, entropy inside the black hole, uh, which raises the quantum information paradox. There's something in quantum physics called unitary. So if I have a specific diamond, its its microscopic states and those all of the arrangements of the particles are always preserved, but the black hole is just destroying all of that. And let's just go to the wait. And the black hole is just destroying all of that stuff. So there's a scientist known as Professor Don Pei. So he says that, I think so, it was issued in 1938 or 1978, the paper. So it talks about a time T page curve. So it should be an inverse W or an inverse V. But what happens? But Stephen Hawking predicts a linear one. And right now, he we think that Don T page is curve is correct, because there are few things called as entanglement islands, which the name is sounds weird, but it says that because the gravity in the black hole is so intense that some specific areas in the black hole are not are connected to the other world, to the systems that are not in the black hole. So it says that if we have a Dyson sphere surrounding the black hole, and we have a very good, super good quantum computers, what what can we do is that we need to collect every photon, everything that is coming from the black hole as a radiation. If we do not even capture a single photon, the calculations will fail, and we we don't get the specific diamond arrangement that we wanted to get. So it's about that. Uh, and by quantum mechanics, it says that the past is connected to the unique future, and by studying the unique future, we get to know the past. So uh, if we do the calculations, we'll get that specific diamond back. So that was the information paradox of the black holes. It's still not resolved. We have a theoretical proof for the uh, Don uh, T page curve, but we still have a lot to discover. The merger of black holes. Black hole entropy measure quantum information gets packed into horizon pixels. The thing that I mentioned, one quantum bit is in is on of 4 pages of blank area, and because entropy scales mass squared, fusing to black hole uh, geometrically explodes the final surface area. Even with mass loss to gravitational waves, the resulting horizon area index thermodynamics disorder vastly exceeds the original combined sum. So, what does that mean? It means that if I have two black holes, let's say that their uh, event horizon area was 10, uh, 10 and 10. Uh, so, what their final sum would be greater than 20. So, that sounds weird, but we can prove that by maths. We can prove that by maths, as we know that entropy is inversely proportional to mass squared. So let's just take two random units, two black holes of equal masses of 10 units, and then we'll get the entropy has 100 units. And what happens is that in black hole mergers, 5% of the things are lost to us in gravitational waves, as you know. So 20, so we'll have the 20 units of mass, and 5% would be lost into the gravitational waves. The final product of the black hole would be 19 solar masses. And now if we get the event horizon, and now if we want to get the event horizon and the entropy of that specific black hole would be 361, because it's 19 squared. So this is a direct proof of how is this thing happening. So now the specific black hole would have more energy, entropy, than both of the black holes combined. So yep, it is about 161 more, and it increases exponentially. Black hole merges entropy considerations. When two black holes merge, the total entropy increases, consistent with the second law of thermodynamics. The final black hole's horizon surpasses the sum of initial areas. So the increase in entropy reflects the irreversible nature of the merger process. So what happens is that it is that now merger process can be not be irreversible. So that is an direct evidence of entropy increase. So uh, and the final black hole horizon, the final black hole's horizon area surpasses the sum of the initial areas. So it's very consistent with the second law of thermodynamics. Entropy in black hole merges. Example: for two merging Schwarzschild black holes, the final area is larger, indicating increased entropy. Spin and charge complicating calculations but follow the same principle related to horizon areas. These calculations support the second law of thermodynamics in dynamic spacetime scenarios. The spin and these charge, these are the two components of the macrostate of the black hole. And what happens is that they decrease our entropy. And why is that? What happens is that when it spins more and more, what happens is it gets bloated, and it's described by general relativity. It's beautifully defined there. And if we get that, we'll see that they decrease entropy, and where the spin and charge are maximum, it's like reaching in absolute zero in thermodynamics. We have not discovered a thermal black hole, and it's impossible. But if we have a thermal exceptional black hole, what would its entropy would be half. Like for a normal black hole, it's 4 pi times mass squared. But for that specific black hole, uh, the entropy would be 2 pi times mass squared. So this is so these two reduce the entropy. And for merging for two black holes, rotating black holes, it's more complicated, and it's described by general relativity. With the example that I just gave you was a special case. So in black when two black holes are rotating, and I was just talking about non-dynamic black holes, but in black holes where they 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 are moving, they the calculations are more complicated. Entropy for rotating and charged black holes. As you can see in the picture, there's the entropy for rotating charged black holes. So Kerr Newman black holes have more complex horizon geometries which affect our entropy calculations. For a Kerr black hole, the horizon's area depends on mass and angular momentum. The formula adapts to include charge and spin, maintaining the proportionality to horizon area. As you can see in the picture, uh, that is the equation for entropy for rotating and charged black holes. It's it is described in general relativity very beautifully. Entropy in cosmology and astrophysics. Entropy is crucial for understanding the evolution of the universe. It helps explain phenomena like the arrow of time, cosmic expansion, entropy considerations, and these are essential in the study of stellar and black hole physics. Uh, okay, so as you can see in the picture, there's the cosmological horizon, and the equations that you see, L is equals to C divided by H. So that is the radius of the whole universe, and by that we calculate the whole entropy of the black hole of our universe. So we use that Bekenstein's formula, Jacob Bekenstein's formula, and we get the entropy as 10 raised to the power of 123 Boltzmann constants. So uh, this black hole equation has the maximum amount of entropy, because in the equation, the uh, if we do not include the mass, what happens is that most of the things are just constant. the 8 pi squared, and all of the other things are a constant. And if we just ignore that, we'll get that the entropy of a black hole is proportional to its mass. So, so that's the case, and it's about, I think so, 30. The constant part, it is about 10 raised to the power of 38 Boltzmann constant. So it's already getting a large boost from the beginning, and the mass, and we, as you know, that black holes are pretty massive, and the mass is we measure it in kgs, so it's a lot. So entropy in cosmological context. So the universe's entropy has increased since the Big Bang. Black holes contribute significantly to the total cosmic entropy. Entropy considerations influence models of the universe's fate, such as heat death. So the heat death of the universe. So it means thermal equilibrium, which means that uh, our universe our universe's entropy would be maximum, which would not allow energy transfer anywhere. So that's the case if our universe reaches heat death, but we are still a long way to go, and we the the universe's entropy, at the beginning it was about 10 raised to the power of 80 something uh, Boltzmann constant, and now most of the entropy, about 99% of the entropy, are in black holes, supermassive black holes, and that's the case because they have the maximum number of hidden microscopic states. So, if we wanted to calculate using that earlier formula, by taking the natural logarithm of W, the number of microstates, we have to look inside the black hole, and which we don't have the correct mechanics for. But if we did, what happens is that the result of the Bekensteins and the earlier formula would be the same. But the thing is that we do not know how will we take the natural logarithm of something that we can't see in. So the difference between these two is like taking measurements from far away and taking measurements while looking inside it. So that's the main difference between those two equations. But if we use that formula, and we'll get the same result, but we need to know the hidden number of microscopic states, which we count using quantum mechanics and string theory. So it's just so this Bekenstein's formula uses quantum mechanics for counting the hidden number of macros microstates. So we are done with the presentation. So are there any questions? Uh, are there any questions by anyone? Okay, math. Okay, expanding of the universe. Okay, so expansion of the universe. People think that it's a result of dark energy, and like people suggest that dark energy might be a thermodynamical consequence of the laws, which states that the entropy of the of the universe should always increase and then reach a maximum. But if the dark energy was not there, what could happen is that our universe could reach infinite entropy. So what does that mean is that the thing that gave you the maximum limit entropy of the universe was about 10 raised to the 123 something Boltzmann constant. But the case now is that the dark energy is expanding the universe. So now we have So like it says that some things are expanding faster than light, and now they are inaccessible to us. So now we have a cosmic horizon of 96.5 billion light years, and now we are taking that entropy density of that. Taking an entropy density of that, and people suggest that the entropy of the whole universe might already be infinite. So, are you getting me? We are just a small chunk of that infinite universe, and why are you paying so much attention to cosmology? Uh, I think so. We should give some attention to cosmology. It's we just I'm just talking about the universe's heat death, of how is that going to happen and how is entropy related to it. So I think so. Did I answer your question about that expanding universe? Okay. Uh, you can also talk with me. It's not like that I know a lot. So, are there any further questions? So, Vriti ma'am, do you have any questions? Uh, so, okay, I think so. There were a few questions, early questions about the zeroth law of, in the case of a black hole. So, so the zeroth law in thermodynamics says that if there are two systems, uh, if there are two thermodynamic systems, and they have a connection with third, and the third system, what happens is that they would be in thermal equilibrium with each other. And when it applies to the black hole case, what happens is that it says that a black hole must also be a thermodynamical uh, entity. So it's thermodynamic. So it has entropy, and it also mirrors. So it also states that this should have an uniform surface gravity because of the thermal equilibrium, and the spin and the charge everywhere should be the thermal properties should all be the same everywhere. Okay, what's how do you know about new things that are being discovered? Aeronautical and cosmology. Okay, yeah. There are you can just search up on the internet and the news. I am not that aware of the new things that are happening about aeronautics and cosmology, and the things that I've talked in this presentation, the Jacobs Bekenstein. It is about almost 80 to 70 years, I think so, years old. So I know there are many more things that are going on, and recently I think so we found some theoretical proof of the Don-T page curve, which uh, which uh, which solves the information paradox. So, astronomy and cosmology, the cosmology is like studying the whole universe, like the early stages of the universe, how it was formed, the beginning, the Big Bang, and the other stuff. Astrophysics and astronomy. Astronomy is like studying planets, solar systems, exoplanets, and astrophysics is something. It involves a little bit more math, and it's about studying heavenly bodies, their physical properties and other stuff. So, any further questions? Okay.
So, thank you so much, everyone. So maybe you will enjoy this session. And actually, he is very younger. Uh, to present his present his in mind and his present all things about the his session. And if you have any question, if you want to talk with audience, don't hesitate. He is very younger. He is grade 8, but he is much interested in science, much and much. So if you have any suggestion, then you can talk with the Aryan. No anyone talk, you can also put in the message. How can explain faster than that? Aryan, आर्यन एक मैसेज आया हुआ.
Okay, how can universe expand faster than light? So the difference between expansion and accelerating is thing that everyone should know, is that we are not accelerating an object to travel faster than light, to take infinite energy to make something do that. But expansion is another thing. It's like we are stretching, and the stretching gets more and more. If we are It's like if I blow air into a balloon, what happens is that it expands, and if I blow it hard enough, what happens is that it expands faster and faster, and with more speed. So that's the case with dark energy, and we have discovered, like with the Hubble law, that there are galaxies which are moving faster than light, and that gives us a cosmological horizon or the observable universe. So I think so. Uh, that's it. Thank you everyone for joining.